Okay, any questions from the last hour or earlier? So I came along in my research career about the time lasers were invented. Spectroscopy changed quickly. I hadn't ever studied spectroscopy, but I got interested in the idea that we could use these new tools, lasers, to measure things. And so I had to start reading books on spectroscopy, and those books had in there information on line shapes. And I got intrigued with the idea that the shape of these lines actually depends upon pressure, temperature, even velocity. And so I got intrigued with the idea that we could use this information now available with the laser absorption measurement to actually characterize the gas dynamic parameters, not just the concentration of the species, but also other properties. So I've always been really interested in line shapes. Lasers get better and better, available at more and more wavelengths. It becomes possible to do this for more and more species. And I'm going to give you some examples in the course of this course to show you how powerful this idea is. People who use pulse lasers, for the most part, don't pay much attention to line shapes. It's something that you need to have a narrow line with source in order to use. So for techniques that require pulse lasers, why would you use a pulse laser? Well, people will use pulse lasers in order to have a very large number of photons per unit time to induce a nonlinear process or to do, say, Raman spectroscopy, which is weak. So those are oftentimes weak, nonlinear, that require large pulse energies. Usually, when the pulse energies are high, this usually means that it's spectrally broad. So you have to be careful. Lasers, not all lasers can do all jobs. But I focus a lot on things that can be done to measure these line shapes. So I want to give you a little background on this and talk about types of broadening. There are different types of broadening. And typically what we'll find is that there are two main types of broadening. And because they both can act in many of our combustion systems, we have to combine those two things into what's called a Voigt profile. And I want to give you some ideas about line shape and then some working examples of why this, to me, is so interesting and valuable. Remember, this is where we were before. This is the fractional transmission of light at frequency nu, monochromatic light, given by this exponential decay law, where we typically assume that the properties of the gas are uniform over some length L. So this is for a uniform medium, path length L, and buried in K is all the information, all the physics, and the sensitivity to a particular species and quantum state. Remember that K is product of some variation of the line strength and phi, the line shape, and we can get S in different forms, but if we took these units here, we would be for B, or we might write it in terms of A. Again, I like A because I know what the units are. So this is a way of relating the line strength to the number density of the species in the absorbing state. Therefore, you can see that K is the strength of this per unit length absorption depends on the number density as well as A. And the line shape function, as we defined it, is nothing more than the local value of K divided by the integral. This way, the integral of phi over the line is 1. So the area under the line shape function is defined to be 1 by most people, not everyone. Okay, so there's different forms for phi. We can do this with units of centimeters, or we can do it with units of seconds. Let's see if I got this right. Oh, yeah. So if I have units of phi, the units of phi are inverse of the line of the frequency type being used. So if we have centimeters minus 1, then phi will be units of centimeters. If I have phi in hertz, then K in terms of hertz, then I'm going to have phi in seconds. We typically use this one. Okay, so this is just a repeat of stuff I've shown you before. Got to be very careful about units. We tend to use centimeters minus 2 forms. Okay, I'm not going to go through this stuff. This is just algebra. Invoke P equals NKT over and over again. You have to remember to use the 10 to the 6 for dynes per square centimeter per atmosphere. Boltzmann distributions over and over and over again. And we have to go back and forth between, if you want to use high-trend database, then you have to be careful about the units again. Okay, how do we measure these parameters? Best way, I think, is a high-resolution absorption experiment. So we'll put some gas in a cell, control the path length, control the pressure, scan the laser across a candidate line, and measure the fractional transmission. Take the negative logarithm, that's now K, and here's our spectral distribution of K. The area under that curve is the line strength, because we integrate over phi. Remember, phi is the K over this. So the integral under this curve is independent of shape and is the very definition of the integrated area or line strength. This is one way to determine S. Now, buried in here, of course, so we measure S, but if you wanted to get to the Einstein A coefficient, now you'd have to put in the number density that you had in your cell. Now, there's different types of broadening. The first one is called natural broadening, and it's the result of the finite lifetime of a molecule in a given state. Another type is called collisional broadening or pressure broadening, resulting from the finite lifetime in a quantum state between collisions. Those two types of broadening, which are based upon lifetimes, are Lorentzian in form, and they'll come to us from what's called the uncertainty principle. These are called homogeneous forms of broadening because it treats all the molecules the same. It's independent of velocity or other parameters. There's a form of broadening called Doppler broadening that has to do with the thermal motion of the atoms or molecules. And that turns out to be Gaussian in form, and it's called inhomogeneous because it depends upon the velocity of the individual particle. So it varies with the velocity of the particles. There's a velocity distribution function, the Maxwellian distribution function. This results in a Gaussian form. The integral is always 1, but in these types, the form of the function is Lorentzian, and in this case, Gaussian. Because these two often combine together in a combustion problem, we have to invoke what's called the Voigt profile, which convolves these things together in a way, certain way, and we'll learn about that. So that's a convolution of Lorentzian and Gaussian. Okay, let's understand the basis of why lifetime comes into play. There's the Heisenberg uncertainty principle, comes to us from quantum mechanics. Again, we just take this from quantum mechanics. There's the combined uncertainties in energy of a state and the time that it spends there is given by h over 2 pi. So we have an upper level U and a lower level L with a spontaneous emission rate A of 1 over tau. Why? How do we think about this? So far, we've been drawing these energy lines as a discrete number, which means that when you take the difference between these two lines, you get a number. But the fact is there's some fuzz to these energy levels as a result of the finite time that they spend in that state. So the uncertainty comes to us from this, due to the finite lifetime that may be due to a collision, or it might be due to the natural broadening. So natural broadening is referring to the lifetime impact of the radiative decay. So if I try to evaluate delta E from this relationship up here, delta E is the H delta nu, where delta nu is the inverse of the time. So whatever the lifetime is, that in the denominator here, that's going to determine the fuzziness of this level. So if you make this time shorter and shorter and shorter, that gets fuzzier and fuzzier and fuzzier. So there's no longer discrete values of these energy levels. They're actually a little fuzzy. Therefore, there's going to be fuzziness in the absorption line shape. So the so-called full width at half maximum is going to be 1 over 2 pi tau. That we call the lifetime limited line width of our line. In general, there's a combination of contributions to this effect, and we have to take into account the fuzziness of both the lower and the upper. So now the combined effect of the fuzziness in upper and lower would be 1 over 2 pi times the sum of the 1 over taus. If the lower state is a ground state, there's no fuzziness there because it's. That's the way to think about the fuzziness of these lines for lifetime limit. How big are these numbers? If we take an electronic transition, which has an average lifetime of, say, 10 to the minus 8 seconds, which would be a coefficient of 10 to the 8, that width would be, in Hertz units, would be here, or in wave number units would be 10 to the minus 4. If we look at a vibrational rotation transition, where the lifetimes are much longer, therefore the uncertainties are much smaller. So typically, vibration rotation transitions are very small. They're typically also much smaller than the numbers I'm going to show you now for so-called Doppler width and the collision width. So you can show the line shape function that results from this effect be shown, and I think I'm going to show it on the next slide, is of the Lorentzian form. What that means is this phi, the integral of which is 1 over a constant, which is the full width at half maximum here, delta nu, plus the distance from line center squared. So it's, in other words, it falls off as 1 over r squared, distance from the line. So the maximum value is given by this simple relationship, 1 over the full width at half maximum. And the value where you're at half the peak is, so you take half, go down halfway, and that width is delta nu n. Okay, now that's natural line broadening, and you can derive this using a simple argument that's based upon a damped oscillator model. I took this from a book written by Demtrotter. We're going to go through it quickly. So basically, this is the equation. X is the positional coordinate of this oscillator. So it's an oscillator that's damped with a parameter gamma at a base frequency omega 0. And that fundamental frequency is related to the so-called spring constant. So if you take this mathematics and you can show that this oscillator with some frequency is going to damp at a rate that depends upon gamma, and the amplitude of x will decrease with time, depends on the damping rate. So if you have a high damping rate versus a low damping rate, you'll get a different kind of a line. If it's a slow decay, you get a narrow line. If it's a fast decay, you get a broad line. And you can show, or Demtrotter showed, how the amplitude can be written as in this form here, with an imaginary term and a real term. And you can argue, or he argues that you finally end up with this term of this so-called Lorentzian form. So all of this is just to show you that when you're lifetime limited, the time dictates the half width, and line shape function is of this form: a constant, and the distance from center squared. Why do I care about that? That's because, first of all, I'm going to show you get the same answer. You get the collisional lifetime has the same impact. Then I'm going to show you when you go to Doppler broadening based upon velocity, you get a Gaussian. So you either get a Gaussian form or a Lorentzian form. And why do you care? Because the Gaussian falls off as e to the minus r squared, faster. The integral is always going to be 1. Okay, so collision broadening, if you've had a course in kinetic theory, you'll recognize this picture. Molecule B moving through space at velocity v. And if it sweeps out a volume, the diameter shown here that is its own diameter plus half of the diameter of the colliding particle A. So you imagine a particle B moving through a sea of A's. And as this B moves along at speed v, it sweeps out an area pi sigma AB squared, based upon, again, the diameter plus half the diameters of A on each side. And that's called the optical collision. It's going to be called the optical collision diameter in our case. This would be the basis of kinetic theory that would explain viscosity, thermal conductivity, and thermal diffusivity. But we apply it here to same effect with photons. Now, from collision theory, you can say the number of collisions that a single B will have with all of the A in this chamber will be the area swept out, which is the product of the volume swept out, product of the area times the speed, pi mu. So this is the volume swept out by a single B per second. How many A's are there in that volume? Well, nth of A. So that quantity together is the number of collisions experienced by a single B with all A. If you have a mixture, you have to sum over all the other candidate A's. And you can then write this in terms of pressure, which we like to do. But basically, Z is the total number of collisions a single B has per second. Why do I care? Because 1 over Z is the average time it spends between collisions. That's the lifetime that it has before it changes its characteristics. That's the time that comes into play in the lifetime limited. So we can use this time, here's Z again. We can use this time and then recognizing the so-called half width at half maximum, full width at half maximum in Hertz units is 1 over 2 pi times the uncertainties in the upper and the lower states, which is 1 over tau, where tau is nothing more than 1 over Z. So this is really Z. So if you think of the units here, this is Hertz, this is C and Z. And since these two terms are taken to be equal in this model, we just get Z sub B over 1 pi. So there we are. If you tell me the pressure, you tell me the cross-sectional area of the AB collisions, tell me the temperature, sum over the mole fractions of A, I can give you the half width of that, of the collision lifetime. This is the way it's usually written. The collision width in Hertz units would be the pressure. This is the way it's in the literature. The pressure times the mole fraction weighted, X is the mole fraction. Mole fraction weighted of A times what's called 2 gamma. That's the collision half width. The full width at half maximum per atmosphere of pressure. So as you double the pressure, you double the collision frequency, and therefore you double the half width. If you want to use centimeter units, centimeters minus 1, you just divide by C. Okay, so that's, because it's lifetime limited, the line shape function is Lorentzian, and now we can write it. It's the full width at half maximum divided by 2, full width at half maximum divided by 2 constant plus nu minus nu 0 squared. I'm done. Tell me the collision width, I can tell you phi. Or measure phi, and I can infer the collision width. And we know that it's a Lorentzian form. Now I have to take into account temperature dependence. So roughly speaking, you can write this 2 gamma term as a function of T, and using our kinetic theory arguments, you can show that it varies with T is something like 1 over T to the square root of 1 over the square root of T. Typical number, if you don't know any better, is that this number is about 0.1 wave numbers per atmosphere. Why do I care? Well, because you have to decide whether this is the dominant form of broadening or not, and it all depends on pressure. Okay, so let's look at collision broadening for some typical gases. So let's imagine pressure broadening of CO. Let's imagine we're looking at the R9 line. Second overtone, 50 ppm in air, 300 atmospheres, 1 atmosphere. So here's a mixture of mole fractions of these species. We have to know the collision broadening parameter for each of these species, and they vary slightly. Then we just execute the summation, and we've got the final full width at half maximum, which is close to my crude number of 0.1. So if you know the mole fractions and you know the individual broadening parameters, I can calculate the collision width. Here's some typical numbers. Here's CO. This is 4.7 microns. That's the fundamental. It's around 0.1. They're generally around 0.1. NO is an anomaly. It's about 5 times bigger than typical. In the infrared, it's about 0.1. So all of these things are molecule specific, and there's varying amounts of literature on these things to look up if you need them. Go up in temperature, what we find, because the increased temperature diminishes the numbers. You can see how these things go from NO here. Let's see, NO 0.14. Goes like roughly like the square root of T. So it depends upon the wavelength and the collision partners. Okay, now The other primary type of broadening is called Doppler broadening. So individual molecules move according to the Maxwell-Boltzmann distribution, forward and backwards, which means that if they can move forward or backwards relative to the incoming laser beam. If they're moving away from the laser, they will see a lower frequency. Moving toward the laser, they see a higher frequency. So imagine you're in a quantum state and you want to absorb light. Well, the frequency required to make a transition changes with the velocity. So that's the so-called Doppler effect, that the change in the absorption frequency depends upon the velocity divided by lambda. Or you want to put it this way, the apparent absorption frequency is the actual value set by the energy levels times 1 minus u over c. You might think that, well, the velocities are always very small compared to c. That's true. But this is enough to cause quite an impact on the line shape. Now, because the velocity distribution is Gaussian, that is the Maxwellian distribution for velocities, random velocities. These are the random velocities. That's different than the convective velocity. The random velocities are given by this Maxwellian distribution where we take only one coordinate x because we only care about the component along the laser beam path. So we know, we can anticipate that it will be a Maxwellian distribution. Since it's a Maxwellian distribution, we will have a Gaussian distribution in phi. Here it is. This is the final answer. Once you know it's Gaussian, and once you specify the half-width, all the other terms are set by the fact the integral is 1. So it's basically constants, but notice the half-width appears here in outside the exponential and inside. Now, this half-width is a function of temperature and the mass of the species, because that came to us from the Maxwellian. Tell me the mass, tell me the temperature, and tell me the line center frequency. I know the half-width. This is an easy one to remember. The full width at half maximum is an easy one to remember because of all of the sevens. 7.17 times 10 to the minus 7, line center frequency T over the molecular weight. Clearly, the smaller the molecular weight, the bigger the Doppler shift. The higher the temperature, the bigger the Doppler effect. So the real question is, okay, there's other types of broadening you might care about if you're interested in plasmas, something called Stark broadening. We won't talk about that. Sometimes you can have instrument broadening. I'll give you one example of that. Sometimes you can use a powerful laser. Somebody asked a question about perturbing the gas. If you send in too strong a light, you actually perturb the populations, and that causes an apparent change in the absorption profile. So there are times when you have to worry about instrumental or laser broadening, but mostly it's not a problem. If you have a plasma, you have to worry about Stark broadening. Okay, here's this example. This might be of interest to somebody who's doing hypersonic flows. Imagine the gas is moving this way. Imagine the diameter of my laser beam is here. How long does the gas spend in the laser beam? V. Therefore, there is a frequency uncertainty that's the inverse, V over D. So it's possible when the diameter is small and the velocities are really high, that width can be competitive with the other widths of collision broadening and Doppler broadening. Not usually the case, but it's possible. Let's look at some examples. Here's a case where we have some molecule at room temperature, molecular weight of 30 grams, 1 atmosphere, electronic transition, 600 nanometers, or frequency of 5 to the 14th. The Doppler width, which is determined once I know the temperature and the mass, and the line center frequency, that determines the Doppler width, 0.04. In this case, the Doppler width will be much greater than the natural line width. The collision width, by contrast, would be about 0.1. So here's a case, 1 atmosphere, representative collision diameters. The collision width is greater than the Doppler by 2.5, but they're similar enough I've got to worry about both of them. So at this temperature and condition, the Doppler width is smaller by about 40%. If I Now go to a row vibrational transition with 6 microns instead of 600 nanometers. If I increase lambda by 10, the frequency is 5 times 10 to the 13th. I now find the Doppler width has gone down. Width has gone down because the frequency has gone down. Here, and now I find that the Doppler width is quite a bit smaller than the collision width. So you can find different relative values at different conditions. Here's another example, high temperature example. Electronic is basically the same column here, but I've gone to higher temperatures. Now I find that the Doppler width is bigger than the collision width. Doppler scales with square root of t, collision width scales as 1 over root t. In general, depending on the pressure and the temperature, you can decide if you're lucky enough that only one form of broadening applies. Why do I care? Because if only one form applies, I immediately know the line shape function. If they both apply, I'm trapped. I have to consider them both. So Doppler broadening is the most significant when the pressure is low, because the collision frequency is low, at higher t and small lambda. Collision broadening is most significant at higher p, lower t, large lambda. So depending on where you are in pressure, temperature, wavelength space. But frequently in combustion problems, we have to do both. And that is done with what's called a Voigt profile. So the Voigt profile is a relationship that combines those two types of broadening in a way that still honors the integrated area as 1, but represents the relative magnitude of these two effects. The Voigt function here is, the black line is the Voigt function with a parameter a called 0. I'll define that in a minute. The Voigt function depends upon two quantities, the Voigt a parameter and the distance from line center, omega. Down here is this a normalized distance from line center. Distance 2 root log 2 distance divided by delta nu d. So always normalized by delta nu d. A0 means, well, you'll learn to mean, is negligible collision broadening, pure Doppler. So there's the Doppler line shape. Area is 1. A of 1 means roughly that the collision width and the Doppler width are equal. Now the integrated area is 1, but it's a lot broader. Why is it broader? Because the collision broadening has a Lorentzian character. As A gets up and the collision broadening takes over, it becomes more and more Lorentzian rather than Gaussian. What do we do about this? So remember, we get the collision width from this expression. So if the line shape function is in terms of the collision width. And we sum this over the mixture as needed. So in order to evaluate the collision width, I need to know the collision widths per atmosphere. That's what is usually reported in the literature. Typical value being around 0.1. You have to guess, that's the value to guess for. This is called homogeneous broadening because it's the same for all molecules. That is, this form of broadening doesn't take into account the velocities. Doppler broadening, we have the simple result right here. Doppler full width, 717, 10 to the minus 7, nu 0, square root of t over m. So you tell me the mass and the temperature. Notice, this one depends only on the mass of the absorber. It has nothing to do with the other gases in the mixture. Typical values, I just did this a minute ago. So typical values are of the order of, depends on the temperature. So room temperature, they tend to be about 0.03, smaller than collision. At high temperatures, they're bigger. This is inhomogeneous, meaning that it depends on the velocity of the molecule. Okay, so now we have to compare Gaussian and Lorentzian. In both, one is this is the Gaussian, and this is the Lorentzian. Remember, the integral is 1. So the Lorentzian being broader, falling off as 1 over r squared, a lower peak. So the ratio of these peaks is given here. So for the Doppler, it's 0.94 divided by its full width. The collision width is 0.6. If you go to the case where the half widths are the equal, which is the example I've given here. So I've gone halfway down, and that peak is the same width as this one. So in the case where they have the same widths, the Doppler line center value is 1.5 times the collision. Gaussian is higher near the peak, Lorentzian is higher in the wings. There's some exceptions that you won't need to worry about right now. There's something called collision narrowing. When you're in a certain pressure regime, as you increase the pressure, the lines actually become narrower. Hardly ever a problem. It does exist. And when that happens, we can't use the Voigt anymore. We use something called the Gladfrey profile and some others. All of a sudden, now it gets more complicated. So you always want to start with the simplest model that's reasonable. But there is a way to deal with this problem when it's a low pressure problem. Okay, so we're ready to go to the Voigt profile. The physical argument that's used is that these effects are decoupled. Basically, you argue that every point on the collision broadened line shape is broadened by Doppler. So it's like, assume these two things are independent, but they coexist. Now, you can argue that the convolved line shape function depends upon the collision value, the Doppler value for u, times the, I'm integrating now over a frequency space, u. Velocity space, excuse me, Doppler space. So basically, at a given value of nu, I have to integrate over the possible values of u, keeping in mind the difference between nu and u. When you do this, we're going to end up with a complicated-looking integral. So it could be integrated. Well, it can be written down like this. Hard to evaluate. So in the end, this tells us that the Voigt line shape function, usually written with a capital V, can be as a function of two parameters. A, which is the ratio of the, usually delta nu n is 0. It's a ratio of delta nu c over delta nu d times square root log 2. W is the distance from line center normalized by this Doppler width. So that you can write this equation in terms of two variables. You tell me A, and you tell me how far you are from line center, and I can tell you the line shape function. So along the way, when you do this integral, you get rid of the dummy variables y here. Okay, so how would I go about doing this? I'm going to show you, kind of lead you through this. So here's the Voigt function. By the way, I've got to be careful. The Voigt function is the term inside these brackets here. And there's a constant outside, which is nothing more than the Doppler width at line center, if it were Doppler only. Okay, so what does this mean? This, remember, I'm going to have the absorption coefficient is the line center value times the Voigt function. The only place where this integral reduces to a simple expression is at the center. The line center, the Voigt function is the exponential function a squared and the complementary error function of a. That's the only wavelength, line center, where you can reduce this down to this closed form. Otherwise, we've got to use a table. I'm going to show you the table in a minute. Basically, what's happening is we change for a fixed Doppler width, whatever it is, that determines this axis. Here's the Voigt parameter, which peaks here for a of 0, pure Doppler, and it changes. The integrated area always being 1. Here's the Voigt table. So you would look this up, or you might have it already stored somewhere. There's a lot of different texts that have this. So the Voigt table is that of the Voigt function. It's a function of a and w. W of 0 means you're at line center. So this is distance from line center, normalized by the Doppler width. This is the increasing collision broadening, the ratio of collision broadening. So over here, we're at line center with a small value of a, so that means this number is close to 1. If we'd have done this at 0, it would have been 1. So basically, you have to, it's just a question of how you access this table. Here's a problem that you would actually solve. You would have to know the temperature, the molecular weight of the absorber, the line center frequency, the pressure, the cross-section, or the collision broadening parameter. You're after the line shape function phi of nu. Here's the Voigt function equation. So the first thing you would do is you would calculate the Doppler width from T and M. Next, you would compute the collision broadening width, which you would get from the two gammas and the pressure and the mixture. Next, you'd compute A, which is the ratio of delta nu C and delta nu D. Now you'll decide, I'm going to vary frequency. Pick a W. For the value of A you have, let's just say your value of A is 1. That value of A, pick a W, say 0, that's the parameter, that's the Voigt function. As you go march in wavelength, the Voigt function goes down and down, remembering it's always going to integrate to 1. That's how you do it. And there are shortcut algorithms, but it all comes back to this expression, which is approximate in the sense that it has neglected the interaction between these parameters. What's happening over time is as the equipment gets better and better, and we're able to measure more and more accurate line shape functions, there's pressure to improve the function. So for example, one popular one now is called the speed-dependent Voigt function, which allows you to recognize that the Voigt function varies with velocity. Of course, every time you add a complexity, add a feature like this, you make it more complicated. But it's always defined so that the area is 1, and it's just a question of calculating it. So what does it depend on? So the line shape function that you observe depends upon pressure, temperature, mixture. Therefore, you need to know those things to calculate it, or you can use your measurement to say something about that gaseous system that is interesting. So Galatry profile is a common one. Different forms of this, collision narrowing. And then there's one called the Berman profile, which is the usual word for the speed-dependent. These are corrections. These are refinements that are only necessary in some situations. Now, another complexity. As you go up in pressure, it's also possible for the line center to shift. That's called the pressure shift. That's usually defined, instead of 2 gamma, that's defined with a delta term. So delta it's a parameter. It's the wave number shift per atmosphere. So you might ask the question, well, why does pressure change the center of the line? You have to go back and look at the properties of the upper state and the lower state and recognize that when you have increasing frequencies of collision, you can change the spacing slightly. So it's a fact. It tends to be small, but it can be significant at high pressures. Here's the typical number. Whereas I told you that a typical number for the collision broadening parameter, 2 gamma, is about 0.1 wave numbers. This one would be 17% of that. So at high pressures, say 5, 10, 20 atmospheres, we usually have to worry about this. So what happens is the lines get broader and broader, but they're also shifting slightly. And if you want to do quantitative work, you might have to figure this out. For the most part, these numbers are not available in the high trend temperatures that we care about. So we usually have to measure these things. Here's an interesting one. This is a good one. This is the Doppler shift. So now we imagine that the incident light is coming this way, and our gas molecule, our convective velocity of the gas is this way. That means that there's a component of the motion of the gas this way, which means that it's seeing a lower frequency. And what that means is if you have a static sample, here would be K of nu. But because this gas sample is moving away, we have to tune our laser further to the higher frequency to get absorption. So in the frame of reference of the moving gas, I need nu 0, but since the gas is moving. Now you might say, well, is this a big thing, a small thing? It can be significant. So that shift can throw us off a little bit in terms of predicting the line shape function. So if the gas is moving this way, we have to really use this corrected line shape function. It's the same area, but it's shifted in frequency. And we can turn that to an advantage to actually measure velocity. I have some examples I'll show you where we measure velocity of the gas this way. Now, sometimes we're interested in measuring the concentration of a species, like the mole fraction of a species J. Sometimes we're trying to measure the pressure of the sample. So we can go back to the integrated area. Remember, the integrated area, one of the systems of units that I've shown you, can be written as SP chi L. Length, mole fraction, static pressure, and line strength in centimeters to the -2 per atmosphere units. So if you want to solve, as we usually do for the mole fraction, we measure the integrated area, we divide by the length, the pressure, and the line strength, which depends only on temperature. And that's how we get the mole fraction. If we know the mole fraction, we actually can use this to measure the pressure. So there's a lot of different ways to use this information. Ways to use it to get temperature, velocity, pressure. This is why I'm so interested in the subject. For example, you might want to get temperature by looking at the shape of the line in a Doppler limited case. So there's two ways to get temperature. Typically, you look at the shape of the line, and if it's purely Doppler limited, the Gaussian character right away, you get the half width and you're done. If it's a Voigt profile, you can still fit it and find the best value of A. And if you know the collision width, you can solve for T that way. But the best way to get temperature is to look at the ratio of absorption in two different lines. So we take the integrated area that we get by integrating the absorbance over the line, divide it by that for another line, write this as a function of T, and we're done, and you can solve for T. And when you do this, you can find that you can measure T very accurately this way. To do the most accurate way to do this is to think about the derivative, the fractional change in R with T. Fractional change in R with T, percent per K. And you can show that it depends upon delta E. So this tells us that the way to do this is to pick absorbing states separated as much in energy as possible for a given species. This is one species. So we've done this to measure temperatures to better than 1%. But you have to understand this relationship to pick the lines. Okay, some examples. Here's an example. Sodium atom, high oscillator strength, 1600 degrees Kelvin. So the question is, we have a heated cell, we know the temperature, we know the total pressure, what's the partial pressure of the sodium. You conduct an experiment and you measure the fractional transmission. Take the negative log, divide by L, and you've just found K. Now, in order to get back to the number density, we have to deal with the line shape function phi. Basically, we have to solve, well, here's the collision width. Since we know the temperature, and I know something about the collision broadening, I put it down here. I can solve for the collision broadening. I also know, what am I doing? I can solve for the Doppler width because I know the wavelength and the mass and the temperature. So I can solve for the Doppler width, and I've also got the collision width. So I know A here, 1.75. Go into the Voigt tables for this A and say at this A and some value of W, that's line center, and I get this number. Now I have the Voigt line shape function for Doppler. I have to have the Doppler one to get the Doppler value 9.39. Now I can solve for the actual one, 2.68, and solve for the partial pressure. So what did I do? We pick a static cell, we measure the fractional transmission of light, we know the wavelength, we know the temperature, we know the pressure. You have to use the line shape information to finally make the quantitative mole fraction. That's the partial pressure. This is what example I like to show. How powerful this idea is. I had a student who wanted to measure the velocity of a gas in a supersonic arc jet, which is it's an electric thruster for satellites. It was based upon hydrogen. So you heat hydrogen, you expand it, and you use that expanded momentum flux to produce thrust. How can we measure the velocity of this sample of hydrogen? We send in a laser light along the axis. This was all done in a vacuum chamber. We send in because this has to be at low pressure, simulating space. We send in a laser light at frequency nu, which we can tune, and we record the light at right angles. What light are we recording? We're recording the fluorescence. So this gas sample absorbs light and spontaneously emits instantly at this angle. And it emits in proportional to the absorption. So if we can measure the spectrum of this light, we can get the velocity of this gas. So we observed in this case that that we had to tune this laser 0.7 wave numbers to match to get to the peak of the absorption line. That shift allows us to calculate the velocity, and it was 14,000 meters per second. We've done this for velocities of up to 15 kilometers per second. And we've done something like this for velocities as low as 5 or 10 meters per second. The idea of the Doppler shift is pretty powerful based upon just the shift of the apparent absorption line. Of course, it only gives you one component. Here's another example I like. Here's a case where we have, I have to explain this now. Down here, we have a vacuum chamber. We have a nozzle. This is choked flow, 0.5% NO and nitrogen. So that's 5,000 parts per million of NO and nitrogen expanding into a vacuum chamber. Supersonic jet. That would be an underexpanded jet. Meanwhile, we have a laser system over here, which is a laser that's designed to give us a variable wavelength monochromatic light in the ultraviolet at a wavelength that's absorbed by nitric oxide at about 225 nanometers. So in comes this laser light. This is some monitoring stuff. In comes some laser light here. And then we're going to look at the fluorescence light, like we did on the last one. And we can measure, let's see if I got this slide. We're going to measure the spectrum that we see, function of frequency, for the flow field where the temperature is about 160 degrees Kelvin, pressure is about 1/10 of an atmosphere. The velocity that we calculate is about 520 meters per second, and here's the measured velocity corresponding Mach number. So here's the signal as a function of frequency. The fluorescent signal that we get. This is the reference beam absorption, so we passed some of that light through a static cell. This gives us the shift corresponding to the difference that's associated with the velocity. That shift was 2 gigahertz, which gives us this velocity here. Pretty good. The width of this, the cell is at 298. That's not so important. We're just using this for the velocity shift. We can use different angles and so on in order to try to get two different components. So basically, it's the Doppler shift. You only get a component. You only get one component for laser beam. A little bit later, I had a student, and we were interested in measuring the mass flux at the full-scale inlet of an Aero engine, a Pratt & Whitney engine. So we set up a system where we use the same thing, but now we're going to do this with oxygen. Molecular oxygen absorbs at about 760 nanometers, just outside your range of vision. It has a pattern of lines that we could go into. So there's a P branch and an R branch of these electronic transitions. Each line is split. So that's the absorption spectrum of oxygen. We take this laser light and we pass it through the flow at two different angles with an included angle of 2 theta. We'd like to measure the flux of air. So we want to know the product of the air density and the velocity. The air density, we know we're going to get this from the measured absorbance of oxygen and an assumption of what the mole fraction of oxygen is. So when we measure the absorbance, we'll see something like this. It turns out, and then we look for the shift, and the shift is kind of small. There'll be a shift between these two signals. They differ by twice. One is forward-looking and one is backward-looking, so you get twice the shift. We play a trick, and we actually do a form of wavelength modulation. Let's just look at these signals down here, beam 1 and beam 2. So we play a trick, and from this, we can get the velocity that's along here, Doppler shift. By the integrated absorption, we get the density of oxygen and therefore the density of air. The product is the mass flux. The target was to see whether or not this optical method would be competitive with the way they do it when they test on the ground. The way they test on the ground is they put this little guide in front, belt, they call it a bell mouth, to control the velocity distribution. They put a pitot tube brake here, and they measure step by step as they change the engine. Change the engine, they measure the mass flux. So we was connected by 30 meters of optical cable, so our systems are in this room, and we beam the light by optical fiber and capture it and bring it back. This is the setup here. These are the two paths that we have. They've configured this thing to give us a relatively flat velocity distribution. So here's the result of the velocity in these steps. This is our measurement. As they ramped up in minutes, their engine, intermittently they would make measurements intermittently. So we measured the density, we measured the velocity, we measured the mass flux. When we're all done, we agreed within about 1% with their traditional instrumentation. But our system would have the potential to be used in flight. Okay, again, I'm going probably too fast, but what did I try to do today? I tried to take you to polyatomic molecules where we have to worry about the number of vibrational modes and the complexities of the structure of polyatomic molecules. I introduced the Einstein theory, which allows us to provide a link to the absorption coefficient and the fundamental Einstein parameter, A or B or F. And then I showed you the power, then I showed you line shapes, and then I showed you the power of measuring line shapes for velocities, temperatures, pressures. So we have an experiment now where we're measuring the temperature of oxygen atoms at up to 10,000 degrees Kelvin. That's the case where they're predominantly Doppler broadened. So the line shape, you need to know it to make quantitative measurements of absorption, and it's a tool to measure things that can't be measured any other way. Okay, so next, we're going to move on to electronic spectra. We're going to introduce some notation again for spectroscopy called term symbols. We'll look at certain example cases called a rigid rotor and symmetric top, and some other cases called Hanson. So we're going to look at the 4 most common classifications of diatomic row-vibronic spectra. And then we'll turn it to a classic example. We're going to spend a little time on how would you do this for OH, sometimes thought to be the most important combustion radical. So how would you measure OH quantitatively, taking all the information that I've given you? So that's like, well, that's not a trivial thing to do, but we now have the tools to do that. So that's what where we'll end up next. Okay? Any questions? Yeah. Yeah. It's only try to remember what Denver said. He's the let's see. I think it's a finite lifetime argument. And so the question is, how do you decide what the lifetime is? So put it expressed in terms of the decay rate. I think that's a simple argument. The damped oscillator is something for which we can solve the equations. It's a way of saying, well, this thing is oscillating away, it's damping. So if it were undamped, it would just stay in that state forever. So that's about a good response I can give you. Okay. But all it is justifying the finite time, certainly principal damping is propensity. And of course, it agrees with experience, so it's correct. Yeah.
Where do you get the cross-sectional values?
What?
Where do you get the cross-sectional values for sigma and this?
Yes, yeah. So basically, they have to measure. They're measured. And so they may have already been measured, or we have to measure.
Is that cross-sectional values like nuclear engineering?
No. Well, the analogy is with the cross.
This is just air. This is just
the analogy, when you do kinetic theory, talk about collision diameters. And you can use that in kinetic theory to solve for the viscosity. So the analogy is now imagine instead it's photons. So the effective area, so to speak. So it's just an analogy with that it's to the right formalism. So then in principle you have to measure it, and because it depends on temperature, you've got to measure it. You've got to also establish the temperature depends. And that's one of the problems with the databases that you're going to access, is there's really not much at really high temperatures. So we tend to measure these things. Of course, somebody may have measured before you and published it. So gradually over time, the literature gets better and better on this question. Yes?
What's the temperature range for the Doppler when you say high temperature?
What's the temperature range for?
The Doppler and
higher the better. Higher the better. It goes to the square root of T. So we've been up to 10,000 degrees. It's hard to produce a controlled sample. But so we use a shock tube experiment to produce slow atoms. We know from our conditions that the temperature is close to 10,000 degrees. We study the shape of the line and we get 10,000 degrees. So it's almost a question of which one is better. What's the signal noise ratio? So how do you produce a known sample of gas at 10,000 degrees to better than say, it's hard to do. How do you do this? So we use a shock tube which has its uncertainty. And then we have the Doppler shape which has its uncertainty. And all I can say is that they agree. And we've done it to 10,000 degrees. Now we do this, well I think I showed in, I guess it's just yesterday, lecture one. I showed the example at the Arctic at 7,000 degrees. But there's a case where they don't actually know what the temperature is. We have to get it there. In the shock tube case at my laboratory, we potentially produce a known temperature and compare it. So I would say, remember now, the Doppler depends only on temperature and mass. There's no collision broadening. So as long as you stay away from the collision broadening part, it's pretty direct. The trouble is, the width you measure is the square root of T. The square root of T is not a good way. It's not sensitive. Line ratios are better. Line ratios are better because you can get more accuracy that way. Square root of T is not as sensitive as we'd like it to be. We can make it stronger. I might have some examples later to show. So we like to use the ratio of absorption in two different lines for given molecules. So it's independent of anything except temperature. You take the integrated area into the absorbances, and it's independent of collision broadening. So you take area to area, it's just temperature. We can get, we've been working on this for like 30 years. The best we've done is probably measuring temperature down to about 7 degrees Kelvin, 1,000 degrees Kelvin. Not always that good. Been able to demonstrate better than 1% temperature.
Yeah, I got a question about the collision diameter. Is that the same concept that people will use in the collision theory for kinetics?
Yes, it's the concept. Right. It's interesting. When you do this, the optical collision diameter is not the same thing as the hard sphere collision diameter that you might use in introductory kinetic theory. So there's different ways of defining the effective diameter. So first of all, the molecule is not really spherical. So it's an approximation. Approximated, you go. So the introductory kinetic theory is in terms of the collision diameter. So that's for kinetic theory. What we have is the optical collision. It's like what happens to the photon when it goes through. What's the cross-section of the molecules for that photon? So kind of it's the analogous thinking, which helps you understand temperature dependence and so on. But it's an artificial quantity. It's just a representation of how is light attending you.
And also, I understand probably the measurement for the optical and the collision diameter is quite different.
They're different. You get different numbers.
Yes.
They're not. They're similar, but they're not. You know, these are artifacts. These are just empirical ways of thinking. You know, models are models, and so you use the model to interpret your reality experiment in terms of something useful, value. So we can have better models for line shape. It's representing the fact that as you change the pressure, temperature, whatever, that the line shape changes. So the experts on this field now are, well, my student who just graduated, he's really big on speed-dependent Voigt profile. As you make the experiments better and better, you can detect systematic deviations in the line shape function. You can attribute to some, but every one of these things gets more complicated. For the most part, for practical purposes, Voigt profile is just fine. You have to do a really good experiment to detect the deviation in the Voigt profile. Any other questions? Okay. Thank you very much. See you tomorrow.